Good afternoon and welcome back to F8. Hope you had a great evening and an amazing start of the day. My name is Desiree and I will be your MC today. Before we begin, I'd like to remind everyone to please silence your cell phones. Please take the time to silence your cell phones. Mano will lead this session today, and here are two fun facts about him. He went 10 days only drinking water, and his hidden talent are his amazing energy levels. Perhaps after this session, Mano, you can give us a little bit of tips on how to replicate this energy and how to survive on 10 days of water. With that, welcome Mano to the stage.
Thank you. I'll definitely tell you guys about that water story after the fact. How is everybody doing? How is FA treating you? Good? Awesome. Good afternoon. I'm Manohar Paluri, call me Mano. And I'm super excited to talk about how we're thinking about content understanding at Facebook. And I have an awesome list of speakers with me today. And I'll introduce them as we go in the presentation. So very excited to talk about this and how it touches every aspect of Facebook and our platforms. So at Facebook, what we're trying to do is we're trying to push the frontiers of AI. And when we're trying to do this, we're doing it keeping people in mind. Whatever technology we are investing and however we are pushing these frontiers, we want to bring back that technology and put people as the focus and think about impact. And in this particular presentation, I want to connect that story with how we are pushing this technology, but also keep on thinking about how that enhances the experience of people on Facebook and its family of apps. So the agenda for today is the following. We're going to talk about extreme vision. As the name goes, it's extreme because in this particular set of efforts, we are going to places in the context of large-scale models, in the context of how many data points we are using to train the models, and many other facets that no one else has gone before. You will see that. We talked about this in the keynote in the morning, and today, especially in this talk, we want to go a little bit deeper and give you all the challenges that we faced and how we overcame it. The second bit is video understanding. If you think about a lot of ways people connect, it's about richer media. And people are moving towards video, 360 video, and more. Last year, we talked about video understanding. And this year, we want to give you highlights of whatever we have done since then and how we are pretty in the beginning of video understanding and how we are building the building blocks for video understanding to take it forward. And finally, when we are thinking about building this technology, whether it's extreme vision, video understanding, and so on, we are thinking about scaling it up for many, many use cases at Facebook. So the best way to scale is to think of it as a platform that any developer can use within the company and even outside. So in the last part of the talk, we'll talk about Lumos, which is our content understanding platform. So that's the agenda for today. We're going to talk about how we push the frontiers. We're going to talk about how we invest in projects that are going to take long-term investments, and we build one block at a time. And we're going to talk about how we scale it for all of Facebook. How did it start? So in our mind, when we think about Facebook, it's the social graph. But when we are building the AI backbone, when we are pushing this technology, we are thinking about it as a semantic graph. So people connect on Facebook. They started uploading, updating their status, uploading photos, some violating our policies, some enriching the experience for everybody, and more recently, videos and 360 videos. So when we think about the AI backbone, the content understanding efforts or the technologies that we're building are basically trying to understand this and then make that metadata available across the family of apps, across the family of products that Facebook has. Now, the newsfeed will get better, search will get better, taking down violating content, policy violating content will get better, and so on and so forth. So this social graph, we are now thinking about it as semantic graph, and over time can build better and better experiences and elevate the understanding of this content and elevate the experience for everybody. So that's the social to semantic analogy. And in the context of extreme vision, we now have state-of-the-art on image classification and image understanding. So we'll talk about that. But taking a step back, we open sourced maskRCNN last year, and this is one of the few models in Vision that can actually take an image, and one single trunk or one single deep net can actually give you classification, detection, segmentation, human pose estimation. This is how we think about many of our problems. When we are thinking about solving computer vision problems, it's very, very hard to scale when we need one model for each of the scenarios. But when we have one universal model, we can do a much better job in an efficient way, in an accurate way, and scale things easily. So in maskRCNN, these are some of the outputs where you can see how detection works, segmentation. In this case, even the small things like knife, the segmentation of the knife on the table is accurate, and you have a bounding box around it. But the same model is actually also giving you these 27 joints on a person that is actually telling you the pose of the person. So I want to emphasize this again. It's one model that is taking these pixels in and giving all of these outputs and giving us a better understanding of what is happening in an image. I want to give it over to Dhruv Mahajan, who leads our extreme vision efforts. Shrep and Srinivas in the morning pointed out that we have state-of-the-art numbers. And in this particular next few slides, we want to emphasize what we have done in large-scale training and how we are pushing the extremities in terms of image understanding. Dhruv.
Thanks, Mano. So let us first look the need to deal with the extremities along different dimensions in Facebook. In Facebook, users interact with billions of images and videos on an everyday basis. Hence, there's a need to train at the scale of billions of images. Moreover, there are billions of posts made every day, and images are captured every day. And these all refer to millions of concepts and entities which exist, which brings us a need for training at a very high dimensional label space. Finally, the data that we have in Facebook is very diverse, and there's a need to train with billions of model parameters or very high capacity models in order to capture all this huge diversity in the data. One of the main problems with the current image recognition systems is that they rely on the manual labeling of thousands of images per concept for training. These images, as well as labels, are then used to train our deep learning models. This approach is commonly referred to as a fully supervised setting. To give you an example, in this case of image of a dog and a cat, if we give this image to annotator for labeling, they will label this image as cat, dog, and floor. Now, at the scale of billions of images, doing this manual supervision is impossible. On the other end of the spectrum is the fully unsupervised setting, in which we are simply given a collection of images without any labels or annotations. The problem with such an approach is that there is a significant reduction or loss in accuracy compared to fully supervised setting. However, if we look, reality lies somewhere in the middle, what we call a weakly supervised setting. As an example, if you consider most of the visual data in Facebook, comes with associated metadata. For example, you always sometimes put caption on the images. In your post, you have text, as well as sometimes you hashtag the images, etc. In this case, for this image, a user may want to give a caption, like a cute cat couple, or might want to tag the image as #cat. One of the main advantages in this case is that this data is available in abundance, literally describes everything visual in the world, and can hence provide a very strong supervisory signal. On the other hand, there's a lot of issues also here. For example, there's a lot of redundant or irrelevant information like cute, couple, etc., which makes the data weakly supervised. We believe that this kind of data can act as a very strong source for training. Now let's look at what are one of the different. On the other hand, there are lots of noise associated with training with this weakly supervised data. For example, a user may give certain tags that might refer to non-visual concepts. For example, when user uploads this image, he might say that this represents #love between a cat and a dog. However, it's a non-visual label which we cannot represent. Moreover, a user may decide not to tag all the relevant concepts which are there in the image. For example, in this case, if his focus is mainly on the cat, he might decide not to label this image as #dog, and hence we have a problem of missing labels. Finally, a user may give wrong labels to the image. For example, he may get confused with the breed of the dogs here and might wrongly say that this dog actually is a husky. All this noise confuses our models and hence poses a great significant research challenge. Another problem with the current approaches is the problem of the long tail distribution. The real world data has a long tail, which basically means that a very few generic concepts like cat, dog, etc. have millions or thousands of images, while most of the other concepts are specific, like particular dogs of the breed, cat, flower, etc., and they will have a very handful of the images to train for. This long tail distribution also poses a very significant challenge for our training. We at the Facebook, for the first time, have trained at a scale of billions of public images that are shared with hashtag supervision. Specifically, we have trained on 3.5 billion images. This training is done at an order of magnitude scale that has ever been done before. We are also able to recognize more than 17,000 hashtags which are present. And also, we are training models with billions and billions of parameters. Our largest model has around 850 million parameters, which is close to 1 billion. Moreover, in order to do this training, we are leveraging the awesome distributed AI infrastructure which we have at Facebook, and we are able to train on around 350 GPUs. I would like to especially point out that there's no manual annotation of the images that we are doing in this case, and also we are not doing any complex cleaning procedures to remove the noise that are associated with the hashtags. Now let's look at some of the results. What we did was we took our pre-trained models and then fine-tuned on some of the popular computer vision public benchmarks for image recognition. Here we show results on ImageNet 1K, which is one of by far the most popular benchmark in computer vision, and the results we got were even beyond our expectations. We got a top one accuracy of 85.4% with our models. To put this number in perspective, the prior state of the art before this has been 83.1%, which means we are reducing the error in our model, using our model by more than 13.5%, which is truly amazing. If we take into account that between these two numbers, the model architectures are different, and then keep the architecture same as we got for 85.4% and trained on ImageNet, we get an accuracy of 79.8%, which means we got a whopping 27% reduction in the error. On another famous detection benchmark, which is COCO image detection, we get a significant 2% AP improvement using our models, which is considered a fairly significant improvement in research community on this benchmark. Beyond posing these, beyond setting these new records, we also have several new observations and learnings from our method. For example, what we observed was that although increasing the size of the data is a worthwhile direction to invest in, choosing the right label space that matches the recognition task at the hand is almost equally important. For example, here what we are showing you is the result of training on 1 billion images, and we chose a hashtag space that closely matches with the labels in the ImageNet 1K dataset. And here we are showing an accuracy of 85.1%. Now let's see what happens if we take 1 billion images, but take a 17K generic label space. The accuracy drops down to 84.2%. This basically means that it is worth investing in the label space engineering approaches where we try to match the source and target label space together. On the other hand, let's see what happens if we increase the visual diversity of our task. For this, we consider ImageNet 9K as our benchmark data set. It consists of 9,000 classes, which is 9 times more than ImageNet 1K, and has much more visual diversity. Here, again, we show the result with the 1 billion hashtags from the 1K ImageNet label space. And what happens is that we get an accuracy of 55.2%. However, in this case, if we now use the 17K label space, which has much more visual diversity, you can see that we get an increase in accuracy. This means that it's worthwhile to spend our efforts in increasing the visual diversity of the label space and dealing with hundreds, thousands, or even millions of labels. This also means that a sufficient effort in the research community needs to be spent on coming up with better and better benchmarks that are more suitable for the evaluation of these large-scale data sets. Now let's see what happens if we increase the capacity or size of our models. Here, I show performance with the model consisting of around 200 million parameters on ImageNet 1K, and we get an accuracy of 84.2%. If we now increase the number of parameters to 400 million, the accuracy improves significantly from 84.2% to 85.1%. This means that even our current models are underfitting, and there is a need to invest more, increasing the capacity of our models. Now, this possesses interesting challenges in terms of systems, computations, as well as resources that we need to address in order to achieve even better capacity or go to higher capacity models. Finally, let's see what happens as we increase the size of our data for this CUP 2011 benchmark, which is a fine-grained data set. On training on 1 billion images, our model achieves an error rate accuracy of 88.1%. Instead, if we now train on 3.5 billion images, we get an accuracy of 89.2%, which exactly matches the state of the art which currently exists, but we achieve it at a very low resolution of 220 cross 220, whereas the state of the art is achieved on a resolution of 320 cross 320 and also includes some more complex procedures. Having looked at some of the quantitative numbers, now let us see the quality of the predictions that is given by or generated by our model. One of the main advantages of using the hashtags is that when people hashtag an image, they typically do it to describe the exact intent behind uploading the image. As an example, if somebody uploads the images of their wedding, the intent is not to say that there's a man or woman in the picture. That is what the current image recognition systems will typically do. The intent to say is that it's a wedding ceremony, there's a bridal gown, etc., and that is exactly what we are able to do by using hashtags. Moreover, if somebody puts this picture of them sitting in the hair salon getting a haircut, the intent is not to say there's a chair, there are women, etc., but the intent is to say I am in a beauty salon and getting my hair cut. Finally, in this image, the intent is not to say I have hair, but the intent is to say I have a particular kind of hair. And in this case, our model is to say, yes, there's a braiding kind of hairstyle that this person has done. These are exactly the fine-grained labels that these hashtags are able to capture, and we are able to capture the exact intent why the users are posting these images. Having looked at some of the social aspects, now look at some of the how this kind of technology is impacting us in our integrity problems. Because we are using very fine-grained label space, we are able to differentiate between nuanced differences between whether it's a breastfeeding picture with the baby getting her feed versus whether it's a nude picture. We're also able to do much better on the violence aspects, where we are able to accurately detect whether an image is violence by detecting whether there are guns, war, or there's a camouflage kind of thing in the image. One of the main, as Shep also said in his keynote, that some of these models have already been deployed in the production. Now, one of the main things we need to take care when we deploy models in production is the computational efficiency. Typically, there are many tasks that require training of the models with Facebook. And if each of these tasks start training their own models, we'll have hundreds of models in Facebook, and each and every image in Facebook will need to be passed through these models, which is computationally and resource-wise infeasible. This is another approach to this, where we here have a single architecture or a single model with different tasks forking out at different levels. This gives us a trade-off. The lower we fork from and fine-tune the models, the more accuracy we get, but the more compute we use because the parameters become different. However, if we fork at the higher level, we use less compute because the most of our trunk is common, but we also lose a lot of accuracy. What our models, which have been trained on billions of parameters, allow us to do is move these points up so that we can get the same accuracy, but at a low compute cost. To give you an example, let's consider this graph for one of our product scenarios where we show the extra computation as a reduction in the and as a function of where we show the error reduction as a function of extra computation. If you look at one extreme where we're doing 100% extra computation, we are getting a whopping 17.5% reduction in error, and this happens because we are fine-tuning our 3.5 billion trained model. On the other extreme, when we just share 8% extra computation, we actually get a 2% increase in error reduction. But what this graph allows the product teams to do is to choose their own sweet spot. For example, if they can say to us that, okay, we can afford 25% extra compute, and at that point, you can give us 6.5% extra accuracy, that would be great. So we are moving towards this universal vision model in which we provide these trade-offs of computation versus accuracy to our users or to our product teams, and they can choose where they want to be. Finally, although we have done a lot of work in this direction towards training on large scale of data, our work is still 1% complete. We would like to extend the number of labels or hashtags in our data further to 100,000s or even millions. And there's a need here and then there's an important aspect here, which is opposite to scaling up efforts that we have done in this work, which is scaling down. That as we go to more and more specific labels, your amount of training data decreases, and we somehow need to work with that. Also buoyed by our efforts in image space, we would like to extend it to weakly supervised video modeling. We would like to extend it to hundreds of millions or even billions of videos. Also, as we just showed, there's a need to increase the model capacity further, and there's a need to invest both on the systems, modeling, as well as computational perspective into this direction. Finally, we have shown that results are still improving if we go to the 3.5 billion scale, and there's a need to increase the data further, and for that to happen, we need to scale our training infrastructure even better beyond 350 GPUs. And finally, I would like to add that the embeddings or the model outputs for most of the public benchmarks will be made available or open sourced. Thanks a lot.
For the whirlwind tour of weakly supervised learning. So to emphasize, this is by far, to our knowledge, the first weakly supervised learning paradigm that is achieving state-of-the-art on public benchmarks. And this is a very good direction, because we can now start dreaming about pushing accuracy by increasing the label space, by going with higher capacity models, by using more data, and by training on bigger compute. This is encouraging, but it also reminds us that we need more fundamental breakthroughs, because just brute force increasing or scaling things will not solve these problems. As Dhruv was emphasizing, we are thinking about video as well in this paradigm. So I want to quickly turn our eye and talk about video understanding. We talked about video understanding last year at F8, where we mentioned some of the building blocks that we were building in understanding the videos. So when we think about understanding videos and, again, bringing that metadata back to enhancing the experiences of people across the platform, this is an example of an output metadata. So what you see here is our technology looking at when people are coming in and going out, who are they, what kind of activity is happening, what kind of speech and actions are happening, and piecing all of this together to really understand the internals of video. And when you do that, you can now do a much better job, whether it's showing the video at the right time at the right place, retrieving it at the right time for the right query, and so on and so forth. So how do you scale to all of the 100% of videos at Facebook? That's a big challenge. If you think about the models that Dhruv just talked about, the video models are even more expensive. They need even more compute. They need a lot more training data. And some of the simple examples are knowing the people, like putting the boxes on the faces, and knowing what they're speaking. And going one step further, these are heavyweight by themselves. But even going one step further, if you think about the activities, which is very critical to keep our platform clean, to actually take down policy-violating content, and to understand at fine-grained, deeper level what is happening in video. So this is an example where we were actually taking some of these models and making them more efficient to run on all the frames and understanding the activity of what is happening. So this was a video that we showed last time. A lot has happened since then. And while we believe a lot has happened, what I want Matt specifically to come and convince us is all the breakthroughs that we have done, but also all the challenges we need to solve going forward. So with that, I want to hand over to Matt to talk about the building blocks of video understanding.
Thanks, Mana. So I work on video understanding, and the first point I'd like to make is just what's up there on the screen, which is that this is a field which is truly in its infancy. And so in light of some of the demos that you've seen, you might say, well, how can you say that? These demos look incredible. And I would agree. But a lot of cases what we're seeing is that we've made huge advances understanding images. And despite this, when it comes to real temporal sequential understanding of video, or maybe because of these huge advances, we're not at the same level. And so if we look at some of the things we're able to do on images now, if you had told me 5 years ago or 10 years ago that I would be doing this kind of thing on a daily basis. I really wouldn't have believed you. We can understand individual frames really well. We can figure out what's in it, who's there. Even in a lot of cases, what are they doing? You would think that detecting actions and understanding action would be a terrific video problem. Well, if you've ever opened Sports Illustrated, you can figure out exactly what's going on from a single frame with no motion information whatsoever. And yet there's this fundamental disconnect because video information arrives incrementally and sequentially. The audio information arrives sequentially, incrementally. And so how do we really confront that? And how do we use that information correctly? And that's something I don't think the field has really come to terms with yet. So let me try to convince you of this in two ways. The first is practical. What is going on here? Well, I've got two frames, exactly a second apart. Did we miss anything in between? You can squint at them for a second. I mean, it's really tough to tell what's happening. You know, is that guy chasing the ball? Let's take a look. Oh, well, of course we missed something, or this would have been the worst setup ever. But it was pretty cool. It turns out it takes about a second to dunk a basketball. I looked at a bunch of different videos before I picked this one. Almost exactly a second every single time, unless the guy is hanging on the rim or whatever. So why a second? Well, if you're processing video a frame at a time, you're not going to process every single frame. You've got to pick some sampling rate. And the trade-off really is how many things are you going to miss when you process at some fixed rate. And so, okay, you could argue, you could say, well, that's the frame selection problem. You know, the photographer who would have been taking photos of this would have done a much better job than your algorithm just did, choosing frames. If he had chosen a frame in the middle, or if he'd been able just to use burst mode on his camera, take a lot more frames, maybe it would have been fine. And I have a lot of sympathy for that point. So if you start thinking in that direction, particularly about efficiency, you're in good company. A lot of recent work in modeling has adopted this point of view. So what happens when a frame comes in? Well, I'm going to explain a little bit just about the current setup and explain a trend in modeling that we've used to build more efficient models. So a frame comes in. Here it looks like we've got some mountains. If you're running a deep net, you instantly extract a whole bunch of feature maps. You run all these little convolution kernels, they detect features. At the beginning of your network, they're looking for bars and edges and blobs and little primitive things. And by the time you're 100 layers deep, they're looking for cat faces and so on. But we extract these feature maps. And then what we're going to do is we're going to use little kernels that cut across, that will cut through this whole thing and look for correlations. What features are active together? Do I have whiskers and a nose, or do I have, sky and birds? And these are going to give us another huge stack of feature maps that model these interactions. And so one thing which isn't quite clear from this picture is that on the right there, in that C2 map, for each frame, for each feature map I've extracted, there's one of these small deep kernels in the middle. And so what is happening is that you're using a ton of compute to model all these interactions across channels. And so this is not a good idea, it turns out, because when you actually look at the activations in any stack of feature maps, it's sparse. There's only a handful of maps active at any given time. And if I give it a picture of a cat versus a picture of a mountain, you're going to see different activations. And you say, okay, well, if I've only got a handful of active maps at any time, let's build that into the architecture. Instead of using these intermediate kernels to model interactions across all channels, let's start eliminating a lot of these possible interactions. And so in this example, I'm saying, okay, we're only going to look for interactions in the first half of the C1 stack and in the second half of the C1 stack. It's never going to interact across, and network's just going to have to figure it out. It's going to have to be like, okay, let me put the cat information in the first half and the mountain information in the second half. And the surprising thing is that it does this. The first time anyone did this, it put all the black and white information in one half, and it put all the color information in the other half, consistently and reliably over multiple training runs. That's pretty remarkable. And you don't have to just go with halves. The sort of this architectural choice you make is like, how many interactions do I need to model? Is it 4 or 8 or 6 or whatever? And you fiddle with this, but you save a ton of compute in doing this. And it's all from this observation that the different channels are sparse, and so you have these different groups of convolutions. Okay, so I went into the architecture there, but what you might say is, okay, if we can actually just make the model faster, reduce all this compute, and get a model that actually works better, why do we care about sequential models? And I want to make maybe a more fundamental argument rather than just a frame selection argument. So a minute ago, I gave you, 2 frames a second apart. What happens if we look at the other case, where we're looking at 2 frames that are now completely adjacent, 1/30th of a second apart? If my task is semantic understanding, and I want to know what's going on in this video, what do you learn from the image on the right that you haven't learned from the image on the left? Almost nothing, right? If you look at both frames, you've learned a little bit probably about how he's moving, how fast is he moving. But I would argue it's completely incremental information, and incremental information should deserve incremental compute. And this is where our current models up to this date have not been cutting it. If you do this with a frame-based model, you forget everything you learned the first time you process that frame on the left, and you start from scratch when you start processing the frame on the right. Our biology has figured this out. Biology strives to be lazy. It doesn't want to spend any more energy computing things than it needs to. And we need to make our models work the same way. This is something we've done a lot of at Facebook. We have a long history of working on video models. It started in 2014 with the C3D model. We took an existing image processing model, brought it over to 3D models, 2 spatial dimensions, 1 time dimension. Used a lot of compute, but it was a successful open source project. 2 years later, introduced residual connections, got increases in accuracy, decrease in compute. Last year, we introduced a particular way of processing space and time separately. So we first do features in space, and then we follow it by looking for how they change in time. This is where you really start to get interesting, because you say, we've actually reduced parameters, and it's easier to train this thing. It's another place where you said these things don't really interact much. And so we're at this wonderful place where you can actually reduce compute, reduce the number of parameters, and increase accuracy at the same time, which means you're fundamentally getting more towards something that's the right way to do it. This was just open sourced actually this morning, so you can go to GitHub and download these models today. And a model we just submitted is this Resnicks 3D architecture, which you may also have heard about today, where we introduced grouped convolutions, reduced compute by a factor of 3 compared to the previous generation, and also increased accuracy. And if you notice, down there at the bottom, there's this tiny little dot where we have the smallest compute. If you compare that to where we were 4 years ago, it's about a factor of 20 decrease in compute, while simultaneously increasing accuracy. Now, I want to tell you one different story, which is that if you have the greatest model in the world, it's no good without data, right? And if annotating images is hard, annotating video is nearly impossible. And so you're almost forced to adopt some kind of weak annotation. And I want to tell this with a story in video. So there's a problem called shot boundary in video. And the question is, did the camera change? And you might say, okay, well, what's hard about that? It turns out it's actually surprisingly hard to get something that really works. Most methods get confused if a flash bulb goes off or if the camera moves very quickly. So we wanted to do better, and we needed a data set. And we said, okay, well, how can we get a data set? If we have all these annotators and they have to tell us exactly where the boundary is, or annotate a range of frames and say there's a crossfade in here, it's going to take forever. So instead what we did is we showed them clips of video, half a second, a few seconds, and all they had to do is say, yeah, there's a shot boundary, no, there isn't, or this is some incoherent garbage. I have no idea what this is. So we did this, and we were able to label hundreds of thousands of videos in 2 days using tens of annotators, which was great in terms of building a data set. But how do you learn from it? Well, we integrated what's called an attention mechanism into the model. And what this is it's essentially some weights that the model learns to assign, and the model says, okay, this is where to pay attention. And so in the first example at the top, there's no boundary, and the network gives sort of equal weight to everything. For a gradual boundary, you can see it locks right onto the crossfade. And for a sharp boundary, it finds the exact moment of transition. And so the point here is not, that we solved shot boundary or that we did an okay job on it. The point is that the scale of the problem forced us to go to weak annotation, and that in turn forced us to change the model architecture so that it could actually learn successfully from weak annotation. And I think that's going to be a more and more important story as we move forward. And that sets me up for this final sort of aspirational slide, which is, what's the natural progression of all this? If we start with weak annotations like hashtags, well, maybe the next step is to learn from text surrounding a post or comments. The next step might be conversations or natural language, and the ultimate step might be just observe the natural world and take all the signals. And so if you were to listen to a tennis video with audio, you'd hear the sound of the ball getting hit, you might hear the player, you'd hear the squeak of the sneakers, and you could ask a model, hey, does this audio match this video? What audio is going to come next? What is this person going to say based on what you're seeing? And it forces you to learn a really rich representation of the world in order to answer a question like that. If someone hits a tennis ball and I play the sound of a snare drum, the model's really going to have to know an awful lot about the world to know that's wrong. And if I show a drummer, they're going to have to know, is it the snare, is it the hi-hat, is it a cymbal hit? So in this way, I think there's really hope to learn really rich representations of the entire world just from watching video. Kids learn language from listening to their parents or other adults or other kids in the kitchen or on the playground. We're finally seeing hope the models should be able to do that. So I want to leave it there and say thanks for your time and bring Mono back up to the stage.
Thank you, Matt, for telling us about various building blocks in video and how we're thinking about video understanding and how we're reducing the supervision. I really believe that towards video understanding, going for video understanding, we need to bring all these modalities together: vision, audio, text, speech in audio, and so on and so forth. So those were like the two technological bits and pieces of what we're doing in extreme vision, what we're doing in video understanding. Back in 2015, when we were thinking about bringing this technology, one of the biggest bottlenecks was how much time it took for anyone to adopt this technology. It could be a very simple thing like, this is a post that is for marketplace. Somebody's trying to sell something and somebody's wanting to buy something. Or it could be something else. So one of the biggest bottlenecks was the product experience needed something, a classifier, but what we were building, the technology was there, but it was not ready to adopt. So this gap was something that we were trying to solve. And as part of a hackathon, which is a commonly occurring thing in Facebook and many other places, we went and built something called, anybody in the company can actually build a classifier within minutes. So if there is no Eiffel Tower classifier, you can actually build it. If there is no this remote classifier, you can build it. And that evolved to not just a computer vision platform, but a multimodal content understanding platform, to a point where anybody within Facebook can now start thinking about building a content understanding model without necessarily understanding all the details. And for that, I want to bring on Don, who is actually leading some of these efforts, and will talk about how we are thinking about content understanding platform.
Thanks, Mano. So in the previous two talks, we heard about technology improvements for understanding content through extreme vision and video understanding. So I'll now talk about how we enable these technologies for use across Facebook. And we accomplish this through Lumos. Lumos is an internal platform that makes it easy for anyone in the company to create content understanding models. So product teams often come to us with a question: how do I build a content understanding model for my new product? Many use cases can be solved by reusing existing tools. For instance, identifying the language of a piece of text, or identifying the top concepts that an image may contain. For other use cases, there aren't any existing models that do exactly what's needed. But we want to help. In the past, this meant sitting down with product teams to develop specific models for their use cases. But as Facebook grows, there are too many product use cases to build from scratch each time. Let's say one product team would like to identify posts about items for sale. Another team is interested in determining whether a live video is about games. And a third team would like to recommend relevant stickers. So by using content understanding models, teams are able to bring their products to the next level. Lumos is a way to scale to all product teams with all levels of ML expertise. Lumos optimizes the end-to-end process of building a model by laying the groundwork for content understanding. This means less time spent setting up basic training and evaluation workflows, and more time spent improving the model for your product use case. The end-to-end process of building and deploying a model can be done completely from the UI without ever having to write a line of code. So Lumos streamlines essential steps for creating a model. We'll talk about 3 main steps: training, evaluation, and deployment. So once you have data for your model, the first step is model training. Lumos makes common use cases easier, like the case of building a classifier on top of pre-trained embeddings. So various classifiers are supported from the Lumos UI, including logistic regression, boosted decision trees, and multi-layer perceptrons. So by using both image and text embeddings, we're able to take advantage of the multimodal nature of problems like post classification. For example, when determining whether a post is about an item for sale, both the text and the image associated with the post can each give insight into what's being sold. So we talked about a basic model. I'll now show 3 more complex model architectures that Lumos provides for model training. The first more complex model architecture is Mascar CNN, which can be used to identify the item for sale from an image. So in this case, a futon. The second model is Resnicks, a video understanding model that Matt talked about earlier. This can be used to determine whether a live video is a video game. A third model type is text CNN, which can be used for classifying a document of text. This model takes advantage of temporal convolution to improve text classification. So from a product perspective, this model can be used to determine whether to show sticker suggestions. So now that we've reviewed how Lumos helps with model training, I'll move on to discuss how Lumos helps with model evaluation. Another function of Lumos is to provide a consistent visual way to understand, debug, and evaluate model performance, as well as to easily compare model experiments, like the ability to view label distributions and scores. So for example, a gaming video classifier would output high scores for the video on the right, since it's pretty clear it's a video game, mid-range scores for the video in the middle, since there are video games about sports, but it's not completely clear whether or not this is a video game, and low scores for a video about an unrelated topic, like the one on the left. So the last step that Lumos streamlines is model deployment to the product. Lumos enables deployment with a single click, so that product teams can also configure specifics around model deployment. For instance, by enabling the model to be triggered upon certain events. For instance, upon post creation, to identify posts about items for sale. So now I'll circle back to product use cases I mentioned earlier to see how Lumos benefits the user experience. The first case is, how do I identify items or posts about items for sale? In this post I created, the classifier recognizes that I'm trying to sell something in this post and shows a prompt to turn on selling features. With a slot tagging model, we're able to go a step further and extract relevant information from the post, including what's being sold and the selling price. So the second product use case is identifying whether a live video is about games. So by correctly identifying more live videos as games, we're able to show and recommend additional videos to those interested in watching, making for a better overall experience. So third is the use case of determining relevant stickers to recommend. So in this product, a text classifier identifies whether M should share sticker suggestions for daily life interactions, like showing excitement. So in addition to model creation tools provided by Lumos, Lumos also provides the ability to monitor online performance and the ability to retrain and redeploy to improve the product experience. So to sum up about the Lumos platform, the vision is to have a platform available for all teams to build products with content understanding in a scalable way such that little ML knowledge is required. It is self-serve to scale across the entire company. The platform works for multiple modalities like text, image, and video. And the platform enables easy experimentation with various model architectures and features. Dozens of applications leverage Lumos, and by making it easier for teams to incorporate content understanding into their products, we can move faster towards helping our community. AI systems that understand content can help with our mission of bringing the world closer together. And with that, I'll pass it back to Mano to talk about our content understanding journey.
Thank you, Don. At Facebook, we believe that our journey is 1%. The progress that you see, while encouraging, we really believe that we are getting started. It's not just because we believe in it, but many of the times we push these models to cases where they fail. There are many cases where low confidence mistakes, there is a mouse in the ceiling, which is actually a bulb, or there is a mirror that classifies as a refrigerator, and so on and so forth. So the current models actually make genuine mistakes that we need to pay attention to and keep improving. Here is one other example where we are actually doing pose estimation, and clearly you can see it's a tough example, but it makes a mistake. So when we are thinking about video understanding, extreme vision, Lumos, all the places, we are really testing these models and making sure we are making progress over time and seeing where these things fail. One thing I want to emphasize throughout, based on whatever you have seen, you really need to understand content to build AI systems for the billions. This makes our community safer, this makes our community more healthy, and enhances the experience of everybody that is using these platforms. And as part of this particular talks, we wanted to emphasize how we are building the backbone, the AI backbone that understands this content and enhances the experiences of everybody on our platform. Thank you, and hope you learned a lot from this talk. Please fill the survey. There's a link there, and I want to thank the speakers as well for assisting me. Thank you.
Thank you, Mano, Matt, and Don, and thank you all for attending. We hope you enjoy the rest of your time at F8.